Well, this one, the off button.
Yes.
I'm just gonna.
Can anyone check YouTube? See if we are live already.
Are we live? Start.
Yes, we are live.
Okay. Good evening, my dear classmates. Glad to see you again because I haven't been coming in, unfortunately. I've been a little bit sick. I am very happy to present to you a paper that I chose called Fast On-Device LLM Inference with NPUs. This paper was actually presented on the ASPLOS in 2025 conference by a group of researchers from the University of Peking in China. I am your dear presenter, Sara. And before we move on to talk about this paper, I would like to introduce myself because probably you've been seeing me on that corner and not knowing who I am. I am a second-year PhD student from Georgia State University. I already completed my master's from here back in 2024. I am currently, thankfully, employed finally, AI data consultant, data science consultant with Guidehouse. Previously, I was an ORISE fellow with the CDC for the NCIPC Center. And my research focus right now, because I like to dabble in a lot of things, is computational epidemiology, disaster preparedness, and injury prevention due to my experience with the CDC. So let's get started. Sorry. So we're going to learn while having fun today. And actually, I was meant to take this out from my backpack. I have a prize, two types of prizes for you. And the goal for today is that we were going to split the room into half and half, but clearly the other half is just team faculty over here. So the rules of the game are the following. We're gonna have 3 rounds, probably more in this case, because now I spread out the questions and I forgot to update this slide. But every right answer that you get from the questions that I ask, you're gonna get a sticker. The stickers look actually pretty nice. If you do ask me a relevant question about this presentation, you get 2 stickers yourself. As I said, the stickers are kind of cool. I hope you can read the little messages. There are about 200, so there's plenty for everybody. Please don't go that ambitious. Then the winning team, of course, if you want to group together, since we don't have that many individuals, or the winner in this case, because we don't have that many individuals present, will get a whole Ferrero Rocher container. I picked the fanciest one that I think is fancy. I hope you guys agree on that. And we're gonna move on to the agenda. So for today, we're gonna go over the executive summary for the paper, the background that is necessary to learn and understand it, the existing research related to it, as well as the novel research direction that was taken by the authors of this paper. Then we're gonna move on to the system architecture, the implementation, the results, of course, criticize it because there's no lack of time for that, and discuss any potential future work that I consider could be beneficial for these authors. And last but not least, we're gonna talk, and you can ask me more questions in the Q&A section. So the executive summary for this paper is the following. The problem that they presented was that they are running, or they wanted to run, large language models, also referred to as LLMs, on mobile edge or devices that are either too slow, require a lot of memory, and they are oftentimes energy inefficient or energy or battery dependent, for instance. Then the proposed solution that they came up with was LLM.NPU, which is what they call the first LLM inference system with efficient on-device NPU offloading, what they mentioned, via prompt and model reconstruction to reduce prefill latency. And that sounds like a lot of complex words that we will go ahead and discuss in the upcoming slides, of course. Now, they did, however, find some good results with their approach. They consider that 22.4 times faster prefill speed for their particular approach for LLM inference, and at least 32.8 speed up of the whole process, end-to-end real-world application. Last, they also, or at least my takeaway from this, is that it was effective in being used to accelerate LLM inference. And not only that, there were other extra benefits such as energy consumption being reduced and memory as well. So the background that you need to understand in order to follow through this analysis with me. Let me put you this example. You are in a pinch, just like how I was with this presentation. And you ask GSU GPT, can you please help me design this PowerPoint presentation that I am clueless about? Of course, GPT, which is on my computer and connected to the internet, replies with, absolutely, yeah, let me talk to your faculty member, let me talk to your professor, their advisor from back then, and of course, the Academy Integrity Fairy. So I, as an example, or imagine yourselves being like, I wish there was something that I could do where nobody can find this out. You know, like I want my privacy. Like how come this GPT knows so much and can share it with everybody else? So I decided that, maybe a mobile device will be my salvation. So I go and I ask mobile GPT, please, I beg you, help me out with this PowerPoint. And unfortunately, the GPT in the mobile device is taking quite a long time optimizing my procrastination as well as trying to buffer academic guilt into myself. So the example that I just gave you is an introduction of the topic, which is trying to understand how we can leverage LLMs for devices that are mobile and in that way promote privacy and as well enhance customization for us only. Now, of course, we have the question of what is a large language model? And that is my first question. And I would love to hear who has this answer for me. What do you think is a large language model? Yes.
High amount of parameters, like from birth, and then like the first one is birth, and then activity. They are much larger.
Good. It is actually a pretty good approach. I am hoping that people online were able to hear you. I'm going to put the microphone here for all those great people. Start passing them around. And you do get to pick a sticker. So we have the first player participating. Thank you. So yes, indeed, LLM or large language models are models that are based on deep learning and that they absorb and train based on immense amounts of data and then consequently produce an output. This output can be text, images, as well as summarization, different tasks that we know of, for instance. I want to highlight that for purposes of this paper, the authors focus only on text generation, summarization, and text-related tasks, nothing of the sorts with images or anything fancy like car detection. I just wanted to highlight that this is actually a slide from our dear faculty, Professor Dr. Alser. Sorry, I stole your slide, but you did motivate me to do this. You said, copy the slides from the presenters back then. It just so happened that you're not the presenter, but you did present this. So as an example, we have the process that the LLM goes through, which is you input data through a prompt, you ask a question, you send information, this data becomes tokenized, which in turn becomes tokens, aka the words get split into sections that are easily understood by the system. Therefore, following that, the LLM creates, or the process creates, embeddings, which is basically a fancy way to say we're going to transform it into mathematical scenarios or values that can be passed through these multiple hidden layers, well, beginning with the input layer, then going through the multiple hidden layers, and then the output layer. And last but not least, after passing through this deep learning model, sorry, I blanked out for a second, you get a response that is translated from a token to a full-fledged human form sentence. And the idea is to replicate how we communicate. Now, there's something that I learned from this paper, and is that I always think of LLMs just as ChatGPT, Gemini, all of these very famous big ones. But there is, in fact, different types of categorizing LLMs. They can be categorized by size, from small to medium to large. They can have, and it depends actually from the number of parameters. So for instance, a small LLM can be 1 billion to 10 billion parameters. Medium ranges from 10 billion to 70 billion parameters. And then large, which is oftentimes what we have for the common description of LLMs, 70 billion to up to 500 billion plus parameters. Examples of the small LLM is Phi 3 from Microsoft, Llama by Meta as an example of the medium-sized LLM, and OpenAI's all the families of ChatGPTs, 4, 5, etc., that are not the mini versions, of course. Then we can also categorize them by deployment style, whether it is based on cloud interaction or interface, edge or on-device LLMs, and hybrid LLMs. And hybrid LLM particularly is quite interesting because you're utilizing cloud, a specific technical situation, sorry, vocabulary is failing me right now, and also mixing them with edge devices. So certain tasks can be sent to the cloud to be performed because they're more complex, while the more simpler tasks can be still performed within the device that you're utilizing at that time. Examples of these LLMs include cloud, for cloud-based, of course, Gemma, which is an example of the edge or on-device LLMs that you will actually see being used in this paper for purposes of results, and Apple Intelligence. But I would like to bring that, yes, Apple Intelligence. And I guess my second question will be, is it really true that Apple Intelligence is a hybrid LLM? Or have we been watching the news lately? Anybody, any takers, have heard anything about whether or not Apple did really develop a hybrid LLM via like that? No takers? Oh man, no stickers then. Actually, they did not. And that was thanks to him because I brought it up. Yes, oh, you did say no.
Yeah.
Oh, I'm sorry, I thought you were saying no as in we don't have the answer. Well, you have successfully, you can always, yeah, you can always guess yes or no, I guess. You can, yep. I hope you like that one. There's variety, of course. Thank you for participating. And indeed, Apple has not yet achieved their promise of developing a hybrid LLM at this time. So let's replace that with Gemini, because actually Gemini has different models that do interact in a hybrid manner. Then we have the by architecture, which indeed includes decoder-only LLMs, which are the most common, encoder-only LLMs, and encoder-decoder LLMs. So you might be wondering, okay, what is the difference between these three? Decoder-only tend to be the ones that can do a lot of summarization, understanding. They're very traditional. They're very robust about doing a lot of tasks. While encoder-only they tend to be good about analyzing information, but not necessarily outputting responses, mostly for summarization. And then we have the encoder, decoder, which I actually forgot, but I'm trying to remember from the top of my head. So since I forgot, I would like to ask somebody in the audience, anybody that has seen this type of category before, would you take it a jab and guess what encoder, decoder actually does? Anybody?
How about the decoder? Like they give the output, you know, take words by words.
Mm-hmm.
Correct?
It is.
So they just search about, they just search word by words, and after that they give out.
Repeat that again, I'm sorry.
They search word by words,
Mm-hmm.
and after that they do output.
Well, that's usually the process of LLMs, but technically the encoder,
Decoder.
Mhm.
I was talking about the decoder.
Oh, the decoder, yes. Yes, it is a token by token, which is word by word approach. You are correct. And since I also don't have the answer to the encoder decoder myself, but you did volunteer at response, you get a sticker. We're gonna move on from this so that my ego doesn't get hurt too much. But next, we have, of course, examples of these types of architectures. Mistral AI as one for decoder only, Google BERT for encoder only, and of course, BART, which is BERT plus GPT as an encoder decoder version. And for purposes of this paper, we are going to focus on small size LLMs that are deployed on edge or on devices, and that they follow the architecture of the decoder only. So next question, what can be a potential problem that you can experience from cloud-based LLMs? Security, yes. Well, we have several ones. I'm giving one away actually with that one. That one happened to me recently. It's a personal screenshot. But what will that represent? Or what are other problems that you experience with cloud? Hmm?
Data transfer is expensive.
Yes, that's another problem. The data transfer is expensive, so you apparently are just collecting stickers. I need the back people to start coming up and with answers. Anybody else? Takers? All right, so problems with cloud-based LLMs are sometimes quite obvious, sometimes are not. For instance, we have the need for computational and memory demands. They're pretty high. We actually have data centers dedicated just for LLM inference, of course. And that also depends on the number of parameters. So for instance, 1 billion parameter model will take about 1.86 gigabytes of space versus a 70 billion parameter model can take up to 140 gigabytes of space. Now, I know we have terabytes nowadays, but that back in my day, that would have been my whole PC. And we also have increased latency, which means that they take a little bit of longer time. It doesn't look like it from the ongoing perspective, but definitely if you compare it with on-device LLMs, because they are right there with you and they just have to send the information to be processed internally, they don't have to connect to the internet and therefore wait for the bandwidth to process the data. Exactly what you said right there, correct? Then dependence on connectivity, which follows through the same path. And then limited personalization. There is a claim that on-device LLMs can actually allow you to do personalization based on your needs versus what we currently have available online, which tends to be a personalization of everything that you all have input at some point in time. Of course, last and my least favorite, because I'm dealing with that every single day working for the government, is that they don't meet regulatory and compliance risk. And in fact, it can be very risky to start asking ChatGPT for help on some sort of project that you may have. So the need for on-device LLMs has risen in the past couple of years, starting from 2022, which is what I have available so far from a beautiful paper that was a comprehensive analysis on-device LLMs, which you will see soon the QR code if you're interested. The increase has, of course, shown, and they are estimating that there will be about more of a need by 2032 for it, particularly in the manufacturing industry, followed by the automotive and, of course, government. Apparently, we do want to ride the wave of AI. And just to kind of remind you what on-device or edge devices may look like, it can be anything from computers, phones, tablets, your car nowadays, and of course, anything like a manufacturing or factory-based equipment, like those that are in Amazon. In fact, I found a very interesting article where Mitsubishi had developed their own LLM, and they found that the accuracy had increased by at the level of 77.2, sorry, I didn't see that number right, %. So this is actually the paper that I was mentioning. And it indicates and discusses that they are, therefore, that on-device LLMs are very great because they're cost-effective, they're compact and faster, equivalent, offline functionality for all of you, so you don't have to wait on the bandwidth to come back to you. And then they are personalizable, and they can enhance your privacy as well, which means that you also have to assess what are the capabilities. They can do UI task automation, such as your one-stop shop for ordering coffee. From the moment that you say that order, it will go and open the app and then select your most common order from either Starbucks or Dunkin', and then therefore select a time for you, and therefore place the order for you instead. Or automated message reply, which is basically elaborate or more of an app level what we currently have with this Siri or Cortana nowadays, but basically it kind of predicts what is your most likely response at that time at a little or a more complex level. And the only problem with on-device LLMs, of course, is that they do still require heavy computation, power and thermal limits, memory, and we therefore need to understand the ways to how to address these demands. And that is by understanding the concept of LLM inference. Inference is the process of coming to a conclusion, an estimated guess. In this case, is the process of using an LLM to generate a response to a user's prompt. And the LLM inference, in fact, for purposes of this paper, has been evaluated into 2 stages, which is or phases, which is the prefill phase, ooh, pizza, the decode phase. Sorry, I get very excited about food. And I'm going to break down these stages a little bit on the high level so that we can all be on the same page. So basically the prefill stage is when you send a prompt such as, oh, I want the LLM to complete this sentence, computer science is, and then it iterates through the transformer models architecture until it reaches or outputs a token, like you said. And that first token comes from the prefill phase and leads to the following iterations of the decoding phase. Every token following after cannot be done in parallel. They actually have to be one after the other until it reaches the end and processes it and sends it out to you in understandable language, human language. Now, this paper that I am going to delve deeper into is focusing mainly on the prefill phase because there is end-to-end LLM inference, and they're trying to basically improve that. Now, their reasoning behind why they chose prefill phase was a little bit confusing to me, but I would like to also give it a guess for you guys. So there comes my next question. Which one of these phases do you think takes the longest? Based on what I just told you, or the order of how things are being computed. Which one do you think takes the longest? Okay. Any other responses? Well, you are all right, and at the same time, wrong. Because it depends, but I will allow you to take one. Who was it? Was it you again? You are just I'm telling you, this whole stack is gonna go to you. Oh, who is? There you go. Okay. Yeah, if you can pass it, just don't take any out. All right, so yes, indeed, when you consider the decoding phase, particularly for cloud-based implementations or LLMs, yes, it's gonna be the longest one. However, the refill phase actually leads or becomes longer when you're dealing with constraints related to on devices, or such as memory, such as the amount of text that they can process. The longer the prompt, the longer it will be, or the harder it will be for them to process it. So the hardware capabilities are one, prompt length is another one, model size is another one, and then workload pattern. Now, while this is not necessarily well linked to what I just explained, I do want to showcase that there is a hardware side to all of this talk that I am sharing with you. And therefore, this is an actual example of what is called a system of a chip, on a chip, I'm sorry. A system on a chip design. It's got the CPU. We all know that the central processing unit is the one that takes care of analyzing, giving orders, following through what's the best pathway for a task. We also know that the GPU is the one that can do actually more complex computations with matrix multiplication. And then in some instances, which particularly for this paper, they use this chip, there are some mobile devices that do have NPUs, which are neural processing units, which are a special hardware specifically for AI and machine learning tasks that can handle tensors. And I remember very well that one of the talks that we had previously, I don't know if the speaker is here, he actually mentioned an approach similar to this, but instead of an NPU, he was talking about a TPU, which was a tensor processing unit. So it is falling in line a little bit with that presentation, but there are some differences, and you will see why. Additionally, before we move on, I would like to mention that the RAM, or the dynamic RAM that these mobile devices do use, oftentimes is called low power dynamic something rate. I forgot, I'm so sorry. They do, or at least the name indicates that this type of storage is actually capable of performing at lower power consumption needs and higher speeds as a result. However, there is a caveat that they are smaller, and of course, they might not be able to transfer information in the same way as a high capacity computer from on cloud devices. Now, moving on to what are the most common producers of SoCs are right now Qualcomm, which is the example we have there, MediaTek, Apple, NVIDIA, and Xilinx, which is now part of AMD apparently. Now, the existing research, I would like to disclaim that I only picked 3 of the many approaches that this current paper could be tackled with, particularly because of lack of time. But there are 3 ways. They basically can improve or speed out LLM inference by model compression, the efficient transformers architectures, or making them more efficient, or via hardware acceleration. For instance, on these 2 papers, this Tilburg, which is very famous because it's from Hugging Face, and as well as mobile LLM, although that one is a little bit more recent, they both had the idea that the small model that they were developing should mimic the larger model's outputs, basically a teacher-student dynamic. And This is called knowledge distillation. And particularly in some of the papers and research results, they highlight that it can reach up to or keep up to 95% of the accuracy of the teacher model. Now, the drawbacks of this implementation. Since we have already been through so many talks, I'm sure there's ideas out there for what could be potentially drawbacks of implementing knowledge distillation. And I know that this was also spoken in another talk about the follow with the term quantization. So if you have a teacher model and a student model, but the student model is only copying the outputs from the teacher, what do you think can go wrong there that can be a drawback in your model? Yes, yes, yes. Oh yeah, okay, where we go? Hello, welcome, surprise. So my question is, given that we're talking about knowledge distillation, where a teacher model sends information and the student model learns from the output of said teacher LLM, what could be drawbacks from this approach? Oh, yeah, the microphone. Thank you so much.
I think like the student model has to see all the data again.
Hmm?
Like student model has to see like all the data, like all the training data.
Mm-hmm.
That's
And
like
that
a bottleneck.
consequently can affect what? If you can't see all the data, if you can't see the knowledge about what is what, like labels, what can happen there that affects at what level is the model being affected? It starts with an A.
If like the predictions of the like teacher itself are not like accurate, so this is going to impact like the student model
Yes.
essentially, and so because it hasn't seen the data distribution itself, so it's going to make biased predictions, and it may add inductive bias.
Mm-hmm. Mm-hmm. Mm-hmm.
As well as we need to know the
Mm-hmm.
if you don't know the architecture, maybe even where the data directed.
Exactly. You are both correct. So you get to pick a sticker and I'm coming after you. Don't worry. In fact, yes, indeed, the knowledge distillation approach has several drawbacks. The most common one is accuracy, which is the one that you disclosed. The other most common one, that is the one that you disclosed, is that there might be biases that are learned by the student model from the teacher model, and that they cannot be corrected because there's no knowledge of the back of the model itself to be able to do so. So congrats, you grabbed two, it's only one. You can't get out of it, you gotta compete with him. Thank you guys, this is great. Huh? Did I? Oh my God, I'm so, which was the other question? Oh, you're setting him up. You're setting him up, okay. That is me. All right, moving on. So just kind of touching on this, computational patterns are unchanged with regards to how things are processed with this approach, meaning that you might be saving yourself some learning time, but if it comes to actually processing the model itself within the device, it's gonna still take the same amount of time for the LLM inference to go through the whole end-to-end process. It decreases accuracy, like you said, because it might overfit from the teacher's errors that it learns. And then it overall reduces the reasoning, the deep understanding, as well as the creative generation capabilities that it might try to develop, which are gonna be lacking as a result. So another way of model compression for this approach for LLM inference improvement or speed up is quantization. And I know that paper, was that your paper? Yes, okay. Oh boy. So I already said the drawbacks over there, unfortunately. I clicked too fast. But the idea is to reduce the bit width of numbers to lower the memory and bandwidth and the computations. Meaning that if you have a high point value or bit operation, you can actually compress it down to a more manageable size, such as integer 8 or integer 4 bits, so that certain parts of your device can indeed do the processing or the computations faster. The benefit of this is that it will reduce, or it may reduce at a greater or lesser level, the memory size of your model and the bandwidth as well. But that's because there are less bits being stored in the memory. Now, the drawbacks for this approach, of course, to speed up LLM inference is that it still struggles with some low bit activations. If it is too small and the hardware that you have available on your device cannot handle it, therefore, there's going to be conflicts with that. There's also going to be the need to careful outlier handling, which I remember very well that was part of your paper, because as a matter of fact, just it's doing the traditional quantization does cause some errors that need to be removed, or outliers need to be removed. And then high risk of degradation and accuracy, like the previous one with knowledge distillation, which is common drawback. Now, the part when it comes to studying efficient transformer architectures to improve LLM inference, we have two papers like long former and reformer. Their idea was, hey, let's reduce or replace components in the models, and therefore simplify or reduce the size of some of the components or the operators. So for instance, if you have the attention element within the layers of the LLM, which I unfortunately didn't show because it is quite complicated and I'm going high level today, you will, as a matter of fact, realize that attention can become quadratic, for instance, n to the power of 2, and it scales out way too fast so that you are not able to handle the capacity or the needs for memory as a result. There are ways via this method to reduce the size of attention layers. However, while you are reducing the model and saving yourself some memory movement and bandwidth, you are setting yourself up for degradation on reasoning tasks of your model. It's going to become harder to train because it becomes unstable as the slopes on the gradients are not as consistent. And then there's going to be weak support in reality for the hardware to be able to run this kind of models. Now, I don't like this approach either, so we're going to move on to that. Now, hardware acceleration, which is my favorite and related to this topic. The idea is that you match the model computations within the LLM to a better and faster suited hardware. For instance, to the GPU or to the CPU, depending what kind of math move you're doing, how many bits or the format of your values or weights are. And then, as an example, I said a heavy matrix multiplication could be sent to the GPU instead of to the CPU because it will be faster indeed to process it. So it allows on its own the parallel computations, lower energy as a matter of fact, because GPUs are slightly more efficient at calculations and performing these computations. And it actually allows for larger models on devices when the memory is handled properly. And the drawbacks, of course, which are not to be missed, is that the hardware is not always available and it varies. As I mentioned when I showed the chip, not every phone has a neural processing unit as of right now. Now, if you are balling in the dough, you might have an Apple phone, therefore you might have an A chip that definitely has an NPU. And those are the ones that can potentially benefit from hardware acceleration in the right set of circumstances. There also are preloaded waves that create bottlenecks. So maybe your hardware is very capable. However, if the information is not being sent fast enough, that is going to present a problem and is going to be defeating the point of having such a fast element or component in your mobile device. Now, software frameworks are lacking or not as strong in this matter because there are not that many to actually promote this kind of implementation. Hardware acceleration requires that you know what and when you're going to send the elements of your LLM or your components, such as operators, again, attention, the QKV, which is the query, key, and value of the ways that you are getting the tokens and representing them and linking them back to what is currently in the background for the information that you're looking for, and understanding it and evaluating it in relation to every other word and token that you have. So if you don't have a software that actually helps you do that, there is really no benefit from hardware acceleration at that point. So the novel research direction that these authors took was delve deeper into hardware acceleration. And by that, they decided to explore new hardware that is up and coming, despite the fact that it might not be available everywhere, with the hopes that it will continue to be more included in the future. So neural processing units are indeed a specialized hardware for AI workloads, particularly for machine learning as well, and tensor processing. They are optimized for matrix multiplications, convolutions, and tensor operations, like I mentioned before. They enable parallel computation on on-device LLMs, because when you have an NPU and a CPU and a GPU, you can actually find ways to overlap them and run them together so that they can therefore process the parts of your large language model that need to be processed. And they also have on-chip memory capacity, which means that they'll be able to access the memory and what is in there faster, which also speeds up LLM inference. So, and as a plus, they have lower power consumption. So the idea of these researchers was, let's take as hardware acceleration via NPUs, but let's mix it up. Let's make a co-design that includes runtime, memory, and model scheduling so that we can get lower latency inference. And as a result, they came up with these three main ideas. They decided that they were gonna make LLM NPU, which is considered the first LLM inference system that is efficient for on-device NPU offloading. And the idea of offloading is that you are taking off from the plate and assigning this part of the LLM to a particular hardware element, in this case, the NPU, in combination with others. And therefore, they compile it together with prompt and model reconstruction as a way to reduce memory consumption, per tensor activation quantization as a way to not compromise accuracy. You're coming back on that. And then dynamic execution scheduling, which is fancy words for, yes, we are having a system that indeed evaluates how things are going to be ordered and where they are going, so that the speeding parallel processing can be implemented efficiently and therefore reduce the prefill latency. So the architecture follows through, which looks like a very complex, beautiful image provided by the authors of this paper. They have the preparation and the execution stage here highlighted, but to give you just a quick overview of how it works. First, the preparation stage is in charge of getting the text that is provided to the on-device LLM and chunking it. So a chunk generator is actually separating this text into what is called chunks or subgraphs. They're called subgraphs because when they're processing this, it's actually common practice to call it a graph, because the compiler's understanding as graphs, despite we seeing them as a transformer model, because of course a decoding-based model. And then, of course, the benefits of this process will go follow through. I don't want to go too deep because there's some slides about it. Following the preparation stage, when they chunk the text, they quantize it by simpling or compressing it down, and then profile the chunks into where they're going to go, specifically what hardware they should be assigned to. they go into what is called a chunk sharing graph execution, which is indeed identifying which graphs that they have created through this process can be shared among some of the elements of the LLM. And we'll go over that section as well because I am seeing confusing faces right now. Next, the execution stage implements what is called the shadow outlier execution, which is a very cool name to say we are removing outliers in a very interesting way. And that is to ensure that the accuracy is not lost when also complementing or compiling this together with quantization methods to reduce the model. Further down, we're gonna move on to the first one, which is chunk generation. Chunking is actually partitioning LLM computation graphs. And it splits the model into hardware-friendly blocks. And then these blocks actually fit, they need to be able to fit in the compute, in the memory, and the bandwidth limits designed for your LLM. I'm gonna ask the next question. Why do you think chunking does this? Why do we need chunking? Right there, guys. But I want a little bit more of an essay instead of just the 2 lines I put there. Efficiency, exactly. So when you do chunking, basically you are shortening the size that is being processed and therefore allowing NPUs to be able to process them or compute those elements. And also for reasons such as limited on-chip memory. You are literally going to get the Ferrero Rocher today. I'm so sorry, everybody else. Up your game, guys, up your game. So yes, indeed, chunking happens first for the purpose of reducing the sizes of the text and being able to process it through the NPUs or CPUs according to what are the needs and the estimates of time that it's gonna take. Examples of this, for instance, we have the group of layers. Now this is we've finally shown the LLM and its famous layers, but at a high level, of course. So we have, after quantization, for instance, you can foresee to find the QKV elements, which usually have linear layers and weights indeed. And therefore, when you are chunking, it finds what are the best groupings to do. Therefore, it identifies those layers are the best to put together, and then it fuses them into one chunk. The same thing for attention. It sees that the manual, the scaling, the softmax, and the other manual that follows after, they should be all put together because they have the same affinities, whether or not it's because they have the same sizing in bits, or they might have the same amount of like computations. And this is done because also NPUs really like to process things in large batches. So by chunking and grouping them together is better than just individually processing the operators within the LLM. Now, oops. The quantization, I need to speed up over here. Sorry, guys, I'm taking a little bit too long. Basically is, as I said, compressing the model. We have in the LLM actually certain stages where it quantizes the information so that it becomes manageable. In fact, when you see the orange and the blue in this graph, the orange is for layers that are floating point 16 or 32, often managed by GPUs, versus integer 8-bit or 4 bits. So by quantizing the layers, or operators in this case, after chunking, they are basically making them easier, even easier for the NPU to process. And it also decreases power consumption as well as memory bandwidth and memory in general. Then we have profiling, which is just the measuring of the performance of subgraphs. I am going to confess that this paper did not provide much information about how do they do their profiling. They basically gave me the magical word of, we apply a heuristic algorithm online. And that was it. And I could not find anything else whatsoever. However, based on what I found profiling is, it is indeed just maximizing the NPU by assigning it to a particular hardware, whether NPU or GPU or CPU, just based on the type of size of the operators or chunks in this case now that there are. So the first key element of their contribution, chunk sharing graph execution. They claim that LLMs have repeating patterns and that attention layers, for instance, and FFN blocks do have some shared similarities in their patterns that could be beneficial to reduce sizing. So since the subgraphs use similar or identical weights, therefore, they came out with a solution that reusing the memory and overlapping computations across subgraphs will be helpful to reduce memory in general. So for instance, in the first section, we have an example of what the usual LLM looks like with a prompt size of 1,024 tokens. This gets chunked into several almost same size, except for the dimensions changing from 1024 to 32, but they all have the same almost elements. These elements might be the same, might not. Some are dependent only on size, some are depending on other elements within the LLM. So the authors decided that those that were only dependent on size and nothing else could therefore be shared between each other. So they came up to the conclusion of the third image, which was, we are going to have a shared query, key, and value linear function for all of these chunks. And that way, we're not storing chunks again and again and again for this first layer, for instance. And then those that do not get to be able to share, they just move on to separate them and calculate as such. Then, of course, at the end, they have some shared linear functions as well that they consider could be also beneficial for reducing the model. So this is their approach to chunk sharing graph. They determined that to prevent any more memory overhead, they will apply this method first, and then basically move on to the next, which is the shadow outlier execution, which basically indicates when to reduce or remove outliers. And what they try to do was that by establishing a threshold, usually of 85% of layers, they will eventually come to the conclusion that most of the outliers that will eventually influence the decisions of the LLM to skew the results in a bad way, they could be removed without actually causing too much of an issue in accuracy. They therefore decided to implement that. And that is also for the purposes of ensuring that when they're quantizing the LLM itself, that these outliers are not causing conflict with the reduction or compression. What they did here was that they evaluated the activations. In some layers, they identified that up to 13% of the layers did not have any significant outliers that could skew the results, and that therefore they were safe to approach this and somehow get a good result. In all honesty, yeah, okay. Moving on. So the LLM NPU implementation is going to be pretty fast. Basic, you know already, the NPU was used, specifically the Qualcomm Hexagon NPU, because it's one of the only mobile NPUs with open instruction set architecture, which they needed to set up all the communications between the hardware, such as NPU, CPU, and GPUs. They use 10 lines of code, 10,000 lines of code in C and C++ in assembly language to be able to do this, and use state-of-the-art mobile large language engines, model engines like LLM, which is basically just a way to say, here, let me introduce this LLM into this on-device in a safe way that it can interact with all of these hardware components for testing. And then, of course, they also use the Qualcomm's neural processing SDK, which is just a framework for them to be able to approach the components for the scheduling of the neural, the operators into the neural processing unit. They use two types of phones, the Xiaomi Redmi K70 Pro and the K60 Pro, because that actually has a Snapdragon 8th generation processor that has the NPU that you saw at the beginning of this presentation. They use both 24 gigabyte RAM memory and 16 gigabyte RAM memory in the hopes to see if there's any significant changes based on size. And of course, Android, because it's the only way that they can test it right now. The evaluation setup, however, they used the following small LLM models, which I would love for you to look a lot and then take a look and delve into this in the future. So if you want to test something out like this per paper, you can. They had used Qwen, which uses 1.5 to 1.8 billion parameters, Gamma 2B, Phi, Llama 2, and Mistral 7B. They also use the LLM benchmarks, which is basically a way to kind of determine whether or not the LLM is performing well or not, such as Lambada, LSWAG, Wino Grande, OpenBook QA, MMLU. And apparently I totally did duplicate over here. So the baselines were, and I don't remember the names, but it's basically the comparable, the baselines are the comparable methods that could be used, such as their system LLM NPU, to be able to determine whether or not it's better or worse than the ones that are already similarly available. They use baselines that were able to communicate with the GPU and establish offloading to the GPU. They use baselines that had mostly, for three of them, was to the CPU. One was to the GPU, and one was to the NPU itself. However, there was a disclaimer where the one paper that they were going to use for a baseline that had the NPU, they couldn't replicate it. In fact, they said that they only based their analysis on the paper's results because it was not open source, and therefore they could not implement it themselves, which I was a little bit, it's a little bit okay. Then the data sets, they use Longbench, Droid Task, and Personal Chat because they offer opportunities to do summarization as well as long prompts so that they can evaluate whether or not on devices can handle longer prompts than what they're usually established. And last, for energy consumption, they just use the Android system power supply and keeping track of it every 100 milliseconds, basically. So the results. In short, they found that for all the individual models that they tested, LLM models, I mean, that their model was successful because it's right here at basically speeding up the amount of tokens processed, as well as indicating whether or not based on the size of the prompt, which was either, or the chunk, which was 64, 256, and 1024 tokens. They also showcase that indeed LLM NPU was successful at reducing power consumption for all of the 5 models that they implemented. And I'm speeding up through here. The end-to-end performance evaluation, these are only just 3 out of the 5 that they implemented because the third data set is not here, was that with a length of 1,451 to 1,672 tokens, their model, which is all the way over here, had a speed up of 6.2 to 26.8 respectively, for instance, with the Quen LLM model. And oftentimes, as you can see, all of their implementation testings were successful indeed, or so they claim. They did, however, discuss that for one of their data sets, because the prompts were shorter, there was not a significant increase in speed in the LLM inference. And they contributed it to the length of the prompt. The shorter the prompt is going to be the same amount of steps and operations that you're going to do. And therefore, the NPU can't really be leveraged on those scenarios because there's still the same amount of time that is going to be performed. There's no significant batching to be able to be faster at processing. So the result summary, the LLM NPU did achieve overall of 2 to 4 times faster inference for them compared to the baseline mobile GPUs and CPUs executions that they had compared it to. They confirmed that chunking, particularly their chunking approach, was effective at reducing memory footprint by 4 times the amount, and that the accuracy more or less likely did remain untouched with minimal degradation despite the integer 8 quantization implemented. They did not, however, go way too much into detail as to how the accuracy was evaluated. They provided results, but they didn't really say in detail their approach to it. The critique. I am going to be honest, and I run out of time, but I have the critique in the top of my head because I am very judgy. And my conclusion from this paper, the strengths of this is that it is indeed successful at speeding up the process of LLM inference by saving up memory via quantization, because although quantization methods that have been presented in the past do have some drawbacks, they are still being utilized because they still, as a drawback, they're not so significant that they might make the model completely fail. So it's best to take that win than rather no win at all. And therefore, if you do need to downsize your models because on devices are of different sizes, quantization is one good approach that indeed, I think it was a great strength to utilize for this LLM NPU system. The sharing, the graph sharing approach that they implemented, I believe that it's gonna have a few setbacks because there are assumptions about whether or not these graphs do indeed are identical, and that for computations that require GPU calculations, the most minimal decimal misinterpretation will indeed skew results. And that will show and accumulate on all of the implementations and calculations continuously through the LLM structure. Because of course they're sharing several sections or subgraphs, right? Overall, the system does showcase promising results in speeding up LLM inference, and it does need some work. The weaknesses is that, number one, they did not account for many or any baselines where NPUs were being used. So with regards to the results that they provided, while it's based on a paper, there is no real time implementation or testing that occur. So there might be some room there for them to evaluate this further in the future. And the biggest drawback from this whole paper, which you probably didn't notice because I hide it very well, is that they did not use GPUs. They in fact use only an NPU and a CPU, and they alternated and scheduled the graphs based on their efficiency, but it only works so well because it was only NPU, CPU scheduling. Once you introduce GPU, things change because GPUs are just as fast, but they're just not as power efficient. So they could have benefited from implementing LLM NPU also with a GPU approach and see if, in fact, NPUs are helping accelerate, or if it's just the same as a baseline GPU implementation, CPU on. So those are my thoughts on this paper. And now we move on to, if the controller wants to, we move on to the the takeaways. Well, actually, I just summarized the takeaways there. The future work. As I said, they should definitely include GPUs in their future work. Make sure, 1 minute, okay, that goes well. And the one thing that I want you guys to take home with when you download this PowerPoint, whether or not you do, is that these are some of the papers that I actually read through that helped me understand these concepts. Because in all honesty, it was a lot of very hard topics in terminologies that were not explained in the paper itself. Take a look at it. All the links are functional, I promise. And then we're moving on to the Q&A, which I already asked for most part, but I would like to open the floor for those who want to get a job and more stickers and maybe steal the Ferrero Rocher from this man right here. Huh? A la 1, a la 2 for questions. And if not, I'm gonna volunteer people. Anybody, takers, any questions? Remember, if you ask a question without me prompting it, you get 2 stickers. You're getting yourself ahead of the game. Any takers? All right, here comes the voluntold. I'm gonna do 2 questions because I know I'm running out of time. So from what you understood in this paper, what are, yes. In all honesty, the paper was quite hard to read because they are not very good at explaining the architecture. The architecture at the end was just the graph sharing that they implemented, mixed with the heuristic algorithm online for selecting the NPU CPU load, where they had in the preparation stage already tagged which subgraphs were going to go to where. And of course, the outlier shadow execution, which is basically just a very fancy way of quantizing the model so that they can also reduce memory while also keeping accuracy. So that was the main 3 contributions of their architecture. And it was mostly a preparation and the ending phase, or like the execution phase, that hosted the outlier execution as well as the graph sharing. But their approach, and this paper in particular, was not as computer architecture oriented as most of the other ones that were presented, in fact. Mostly because they try to cover too much. They try to tackle way too many things to benefit LLM inference at the same time. So they did not indeed go into much detail other than the quantization operations that they did, which I did not share with you because time in, as well as mathematical difficulties on my side. But definitely that, I hope that answers your question. You get 2 stickers, by the way. Yes.
You mentioned that they did not use the.
No.
And also you said that they are related about quantization, reducing the data size. So is it like hardware level optimization or software level? If there is hardware level optimization, you mentioned that NPUs more performing better than GPU, like that, or?
So the question, let me repeat it because I realized that we don't have the microphone while going around. I'm hoping those online can hear me because I'm pretty loud. The question is that you're trying to figure out whether or not the adding the GPU will in some way change the output of, or the results, as in like, is it going to be better or worse than NPU implementation? Is that kind of where you're trying to get at?
new hardware includes the new hardware. Not very new or interesting, but my question is NPU is like a new architecture, then company to other CPU, or it is just a software module that is optimized in the
So I'm still a little bit confused about your question, but I think that in my perspective, since new hardware is coming up and NPU architecture is improving as it grows, of course, there will be a point where NPUs will definitely have more advantages than maybe GPUs for purposes of mobile devices, for instance. Already is showing promising results with power consumption. As I showcase a chart actually that show like the comparison side by side of CPU, NPU, TPU, and NPUs. In general, what they actually pointed out is that for now, NPUs are better at doing integer or math operations. So more complex or longer operations or that require more data to be processed or larger weights, like that will be better suited for a GPU to handle and compute itself. So they could have included that in their method by utilizing the GPU and handling those scenarios better with the GPU itself instead of the CPU, which was defeating the point of the whole NPU structure because they couldn't quantize every single layer. There had to be some layers left in 1632 floating point bit format. I hope that. Thank you, everybody. Sorry I tortured you so much, but oh, you get through because you asked the question. All right, I guess now we're gonna do the win. Who's the winner? We know who's the winner. He's literally showcasing his winnings over there. Congratulations. So yes. And you can share the whole. And I open the floor for those in the later on. I'm gonna pass this around because you guys can keep some stickers. They're pretty cool. Just leave me one or two for my child. Huh? It's like a very cute pictures of like. All
right, guys. Now we have two options. Either we start the party, then we continue with the talk, or continue with talk. Whatever you choose.
Can I take a cookie? I'm so hungry. I need water.
Stop, take picture, or continue with the talk. Maybe after second talk, first talk. They have a request. You want to start? Up to you. I'll leave it up to you guys. Sorry.
You might want to turn around.
That's me.
That's us. That's us with the candy. Thank you, everybody. I don't know how you handle this, but. Color. I need water. My throat is so dry. I really need to go drink water.
Can you hear me? Dulce, can you hear me?
Yes, we can hear you.
Right now.
Right.
But how's hers talk gonna be that loud?
Dulce, can you say something?
Hi. Can you hear me?
Can you hear?
We can put the laptop. Not that this is not. This is,
Maybe, can you keep saying something?
Um,
Why is the thing coming from the laptop?
introduce yourself.
Hi everyone, my name is Dulce.
You can hear? If not, please, you can join the Zoom, okay? Then you can hear it directly from laptop. Maybe one of you can do it. Maybe we'll have some echo. I don't know. Let's see how it goes. Okay, you can start.
Oh yeah. You got it.
Dulce, you want to get started?
Yes, I can start. Hello everyone, good evening. Thank you for being here. My name is Dulce Osorio, and together with my teammates, we'll be discussing an interesting topic from computer architecture, which is linear compressed pages, which is LCP for short. Bef- Before we dive in, I'll give a quick overview of what the paper is about. The problem is simple. Modern programs are getting bigger, and we also run many programs at the same time. So memory demand keeps growing. Traditional memory, can you click please? Traditional memory compression does save space, but it often slows things down because decompressing data takes time and makes memory access more complicated. This paper proposes linear LCP as a solution because it keeps compression simple, predictable, and fast enough to use in real systems. So continuing from the introduction or from the previous slide, this slide summarizes the big picture of why LCP is even necessary. Memory demands keep growing, but DRAM is expensive and uses a lot of power. So we can't just keep adding more. Older compression methods try to help this issue, but they introduced delays and made the system more complicated. LCP offers a more simple fix by keeping all compressed pages the same size. That makes addressing easier, reduces overhead, and keeps the system fast and energy efficient.
So, oh, sorry. So you guys be wondering, what is the point of this topic, right? Why are we sitting here talking about something about memory, right? The main issue is it actually affects all of us sitting here, right? In some way, shape, or form, many of you guys have done large data projects. I'm pretty sure people who used Mario Quebec's LLM class in the spring, they definitely had issues with it. But a lot of memory is being utilized, and it's obviously taking a toll on how the bandwidth and the latency of how certain applications are working with, right? The whole point of this paper is essentially analyzing how compressing the memory per se can help optimize how certain storage is moving on, and obviously, you know, making sure energy is as efficient. Yeah, and while keeping with the whole compression process going forward, it still optimizes the operating system. So essentially, there's no kind of delay with it, but essentially helps compress data and helps us keep things moving forward, essentially.
So guys, before we start the paper, we have some basic terms. Those terms are going to repeat a lot throughout the whole presentation. So we just want that you guys have little basic understanding what that word means. So Dulce, if you know that word is going to be pretty simple. You can answer it within the 5 seconds, otherwise the answer will appear anyways.
Anybody have an idea what RAM is?
So guys, if you answer it even one sentence, you'll get a piece of lunch. Simple.
Random access memory. One pizza for it.
Yeah, I'll remember it who's saying it.
What's DRAM?
Okay. What is useful for? Like,
What will be the benefits and use cases of it? Next slide.
this common type of RAM, it's slower but cheaper. We have cats. Everyone should know. Let's see. Right, lights. Latency. Right. And we have bandwidth. And we have energy. That's the memory energy.
Energy consumed during data transfer.
That's like 3 slices already.
Raw form. Yeah. Have compression. Okay, nice. This is basic, simple English, guys.
Yeah, it's basically because to get a general idea, because most of these keywords are going to be repeated throughout the entire paper and explanation. So getting an understanding now will help if you guys have any questions and clarifications.
By the way, this is one of the like initial C, which is like compression size.
Data of the data.
Run. They're wrong. We have case table entry.
What does the data?
Any guesses?
Like dictionary?
I mean, it's kind of wrong, not wrong. Dictionary where the information about the pages, yeah.
FTLD. No one knows this one, huh?
Wow. One whole pizza.
Yeah.
One whole pizza.
Actual address of the hardware. Fragmentation.
You're gonna be out of pizza. All right. One of the big concepts that a lot of people don't understand is why are we focusing on memory compression, right? If you're telling me that nobody else has implemented certain features, right? There have been, right? This is a clear direction of an example of where it has, and it's known as cache prefetching. Essentially, what it does is it essentially reaches out to the CPU and tries to see using a predictive analysis to see, oh, it might need this page, it might need this information, and act accordingly, right? But the downside with that is that because of its predictive analysis, it won't be 100% right trying to analyze what might be going next, right? And even with that issue is the bandwidth, right? Due to its limited constraints, it's essentially not able to have higher bandwidth. So essentially, if it hits, it actually ruins the bandwidth and obviously the speed at which it transfers data. Another approach was memory tiering, right? Essentially, a good example would be getting hot data like the pizza and cold items like the cookies and trying to isolate which needs to go faster, right? Obviously, fresh necessary data is going to be important. That's going to be the fast approach. And cold approaches, which that could be taking its own time, is depreciated on its own aspect. The issue with that predictive analysis is that it's not able to identify what is hot and what is cold. So essentially, it hits a Medlock bridge in the sense that it won't be able to identify it and causes issues, right? And again, with this second approach, it obviously affects latency reduction and affects bandwidth as you move forward.
Here we see why traditional memory compression is so difficult. There are three main challenges. The first one being page mapping. In page mapping, compressed pages become different sizes, but the operating system expects pages to be uniform. Once the pages are different sizes, fragmentation starts happening, and small compressed pages don't line up nicely in memory, which forces the operating system to track lots of irregular space fragments. That makes memory allocations and page migrations more complex and expensive. Then we have challenge number 2, which is physical address tags. So here compression moves data around, but caches expect memory locations to stay still. Since compression moves them around, it confuses the cache. So in other words, caching is fast because it quickly matches addresses, but compression slows it down due to it moving data around. Then we have challenge 3, which is cache line address computation. Each cache line compresses to a different size. So the system must calculate each line's position by adding all of the previous line sizes. And this can take up to 22 additions just to find one line. So in other words, in every memory line, it has different sizes. So you can't just jump to the one you want. You have to count through all the earlier lines, and this also just makes compression more slower. And with all this being said, these challenges make older compression systems slow or too complex. Before we move forward, I have a quick question. Why does compression make memory page mapping harder for the operating system?
Guesses?
Repeat it.
You can click next so that it can pop up. Sorry, I put too many animations. Click it again. Any guesses?
Because of index. Right?
What happened?
You said
Because of indexing.
Index.
So, nice guess. Because compressed pages become different sizes, and the operating system normally expects all pages to be uniform, this complicates managing memory.
That's what she said.
So like, what is memory compression, right? So basically compression makes anything, for example, imagine a local train, right? It's a one physical box where everyone gotta go inside. So usually supposed to be like subway, for example, right? It's just meant for specific X amount of people. Like, and then because of some population, it's more than the people who are supposed to sit, right? So it's basically we are compressing inside the one local train. Next. Let's click on screen. So like, yes. So when squeezing and unsqueezing takes time, and so the space saved needs to be worth an extra work, right? Because it's hard to go, get in and get out when it's so many people. So it lets that specific object hold more in the same amount of space. And railway is the best example. Next. Let's click arrow. Sorry. Okay, so we have a little activity to do, and we need some participations. So if you don't want to answer any question, you can participate and get a slice. Right? Okay, we need few guys, at least 5 to 6 will be all right. Anyone? Just pull up, guys. 4 slides.
Ladies.
Yeah. Equality.
Untrue. Nancy. Ranavi.
Let's go. We don't have time, guys. Okay, so for the first try, all they gotta do is they gotta stand on this paper with both of their legs on it. Okay, and that's a simple task. And we want to see after if all of them gets in, we want to see how many more people can get on it. Yes.
All of us
Yeah.
together. Yeah. Tell us. Tell us. Naeem.
Nine, the whole phone. Yes. Yeah.
Not partial data, full data.
It has to be. Let's go. Let's go.
खड़े हो rules चाहिए पहले.
So you see, like it's not. You see, it's not happening, right? So
Yeah.
go back. Now what you can do is now you can use only one leg and you can put the foot on. Just one leg, but the other leg has to be in the air.
In
So
the
make
air.
sure you're
Other
technically
leg
on
in
the paper.
air. Naeem, other leg in the air. In the air.
Okay, nice. Okay. So the purpose of this activity, thank you guys. Guys, earn yourself first. You just throw it in the press. So basically of this activity was basically trying to say that, for example, when they first tried it by their own physical, same physical size, right? They put it both, they tried to put the both bits, but they couldn't like manage it on the same size. But what they did, they compressed themselves in a 1 foot, and now they're able to exist on the same page. So that basically explained the concept. So now we understand that what the compression is, right? We had lots of previous papers, previous approachers. We're gonna talk about them. The first one is IBM MXT. Does anyone know what the full form of MXT is? Nah. Clap for effort. Thank you. So it's memory expansion technology. So the way this process works, that they had to build like a physical structure in their hardware, and what it does that they have, for example, this is the processor, and this is the cache, and then here's the compression DRAM, right? The DRAM. So then they have created here the 32 megabyte cache. What it does that it saves your frequent used lines or pages basically. And what it does that now the system don't need to compress those information which you frequently use it, and the rest of the files or the pages that you're not using it, it'll decompress it and it'll put it back all the way to the DRAM. So that was the first time someone tried to solve this memory compression kind of like topic, I guess. And then they used the LLMs compression, which is like the 64 cycle decompression, which is quite big. Next slide, please. And so in this approach, there are like two scenarios. If it hits, then it will be here. If it don't hit, then they gotta go all the way till here, decompress it, compress it again, and pull it back all the way to the main memory. Next. There are some advantages and disadvantages. The advantages is that it hides decompression latency. Basically, that when it hits in the first time, you don't need to go all the way to the back. That's why it hides the decompression latency. Then the operating system don't need any modification because it's already physically in the hardware. And the third one, it's good for high locality workloads. Basically, for example, if you're accessing the same 20 MB data sets to run your R query or Python query, it's really useful because then you're using the same data again and again, which is already in that 32 megabyte. I mean, it's quite smaller compared to today's computers, but at the time it was a big deal. The limitations we have is it's like the high area cost. Basically, you're creating a specific designed hardware for this one topic. Then you have a high energy consumptions because you are already fitted that 32 MB cat inside the software, so it takes energy and it consumes more. And the catch misses incur expensive decompressions. Basically, what it means that, and if you don't hit your information, for example, if you don't hit the second scenario, right? And you will not gonna, there will be lots of scenarios you will not gonna hit it. So basically they gotta do the whole process and they gotta pay for that whole process eventually. So what they were doing it here is they were just getting lucky, right? If you get lucky, if your information is here, you're saving basically like you're hiding the decompression latency. But if you don't hit, then you gotta spend all that energy or whatever that 64 cycles it takes to decompose compressions. You gotta do that anyway. So it wasn't solving the problem. It was just fixing it for a bit, I guess. So then the other guy comes after this one, right? And they tried some other way. And their way is basically what they does is they have this block size table which stores the, one second. Think of BST as in like the specialized cache that holds the compression information. And that's the double size of TLB that we talked about the basic terms. And the hard part about this process is it's speculate address computations on every LLC access. So then it saves every time it goes. Doesn't matter if you miss or you hit, it'll gonna save you on every miss and every hit. And that's causing, like that's one of, we're gonna see in the next slide, that's one of the problem for this method. And it's used frequent pattern compression algorithm, which we're gonna talk about in upcoming slides as well. So here's the scenario. If L2 missed, then what happens in this process? Before, if it was missing, then it was doing the basic thing you were supposed to do. Here, what it does that it'll go for L2 to look at for that data. At the same, the BST will look for the data while one second. The L2 catch is accessed to see if the data is there, and the BST starts computing the physical address in case we need to go to the DRAM. So it does this both things at the same time. Next slide. So that's what I was trying to say, that on L1 miss, BST accessing the parallel with the L2 catch. And it requires up to 22 integer additions based on the author who tried this method in 2005. And it hides latency through speculations. Basically, the way they hide the latency, it's different than the first approach, because here they're already counting those previously line size. So what happens then when you want to find that line, it's gonna sum up all the previous lines. We're gonna talk about it later on, like traditional way and the new way. And then it will go directly to that memory, which is already counted on every hit or misrun. Next. And then we have advantages and disadvantages. As I talked, is better space efficiency than MXT. Here's no any specific hardware design for specific one thing. And FPC achieves like 1.59 compression ratio, which is really good as well. Like imagine your 8 GB RAM goes to like 10 or 11 GB, which is without using any additional software hardware, I mean. And it attempts to hide address computation latency. The limitation is speculative computations on every LLC access, which I just talked about like 3 times. And then it's significant energy overhead, which is 6.1 versus the baseline. We'll talk about that later on. Next. So now the main main topic comes of this paper, which is the LCP. And the way the LCP works, for example, like we previously talked about 2 different approaches, and it was quite complicated, right? It wasn't that simple. So the third approach has to be more complicated, but it's not actually. It's really simple. What they does is they're gonna make all that lines in the same size byte. So for example, if there is like line 1, line 2, line 3, L4, L5, we're gonna see, right? They're gonna only takes the ones which have the same size after the compression, which will be like 16 bytes, 16 bytes, 16 bytes, 16 bytes, 16 bytes. And then what it does that if you wanna find that line, you just gotta use the index number, right? And then times the byte. I'm gonna show that to you and later on. So the traditional way, they count those goes to that physical address is they had to remember, which was our second approach. They had to remember all the previous size lines numbers, and they sum up to it. So if you want to go to the line 10, you gotta sum up your line 9 size, 8 size, 6, still 1 or 0, and then you go to that 10 line. But in this approach, what they does is because all the lines they're making the same bytes, what it does that it's just gonna be like, what was the index number? If it was 2, then it's like 2 times 16, which is what? So it's gonna take that much amount of bytes to go to that line, which makes that process to big of 1 complexity, and the other one was big of n, because of course you're summing up. And the good thing about that is like in the computers, like multiplication is just one simple thing, so it just keeps the complexity to 1, big of 1. And here are some examples that I was talking about. For example, if you want to go to, first of all, it converts each page into like, if the page size is 64 bytes, it'll convert it into 16. So the ratio is 4:1 compression. And for example, if you want to find line 2, then it will go by 2 times 16, which I just did, which is 32. And if you want to find line 37, then you don't need to like sum up all the previous ones like the traditional way. We can just like be like 36, 37, which is the index number times the size of bytes, which has to be the same for each line. And I don't know how much multiplication. Which is 592 bytes. Not good at math. And here's the formula, which is catch line index times the compressed size. Its consistent time is big of 1 regardless of the line position. Single shift operation in hardware, no data dependency, no SQL processing required. Next. And the fast part for this, the hit and run kind of scenario here, not hit and run. If it hits or hit or run. Okay. Scenario is like if it hits, then it computes the offset, and then it's just gonna count the index number times the compression size, and it'll go to that specific address, and then it will fetch from DRAM, and then it will come back, and it will decompress while taking the metadata at the same time, which is really faster than compared to the other approaches we had it before. Next. So this is the common case which happens most of the time, since exceptions are not that much in each page. So the line compress, it decompress, and that's done if it's the common case. And because of that, the latency, the time complexity is just going to be 1. And then we have the exception case, which happens 20 to 30%, actually less than that. On average, it happens for 17. We'll see in the upcoming few images. And it's basically, it does make that work a little bit more, but not that much, because of, as you can see here, it says the metadata shows exceptions fetched from region 3. So we don't know what region 3 is in the upcoming slide. So now it have its own 3-layer structure. The way it works, for example, the first layer have all the same number, like same amount of compression size lines. So for example, if there is like 6 lines, this one have 16, this one have 17, this one have 16, this one have 16, this one have 20. Actually, it don't happen. It will be double or different number. And then this one have also 16. Yeah. So what it does, there is the first stage, right? What it does, it will gonna pull all those ones which have 16, and then it will put it in the first region, which says n fixed size slots, all slots same size of the C, which is the compression size. Then size has to be n times C bytes. The second region, what it does, that it will gonna create an exception sitemap. Is basically 0, 1, 0, 1 scenario. If it's 1, that means there's exception. If it's 0, then it means it's a good, it's the same compression size. So what it does, then here we saw that it's a 16, 17, 16, 16, 20, 16. So this one is exception, this one is exception. So what it does, it just creates the array, which is 0, 1, 0, 0, 1, 0, right? So we know this one is exception. And that's what that second region does. It says identified exceptions and located region. And what also it does, that now it's gonna create the exception indices, which is basically it's gonna be like, okay, we found our first exception at line 2, so we're gonna say line 2 it equals to the our first exception, which is exception 0, since this starts with index, right? Go next. And now we have the region 3. What it does, it stores those values which is created by region 2, and it will be like, as you can see in the picture. Next. So I basically just talked about whatever is written here and like regular human way, but this is like really formula way of written it here. No question? Any question so far? Understand it?
How these like exceptions like 17?
If it's different size, there. So the simple rule for process is all line has to have same bytes. If the line don't have, because like some lines can be compressed, right? Some line can be compressed, so that's exception. Some line have different size compared to the whole group, that's exception, right? So if it's the same size, we'll keep it for the first group, and the rest remain is exception, which is very, very rare happen. But we'll see it. Any other question?
Because essentially, if it can be compressed, it will get into its slot. But if it's not compressed, it becomes an exception, and it goes down like a flow system. It enters stage 1, then stage 2, and then stage 3, as mentioned here, is exception storage, where we can come back and see what wasn't able to compress. This process kind of helps prevent us have to go back and forth with the DRAM, essentially. Yep. So when we looked at the other two approaches, right, we were obviously looking at, as Jay drew here, with the 32 megabytes and constantly going back to DRAM. That poses the question, what does it do with the operating system and the cache in general, right? Essentially what it does, it kind of helps eliminate certain complexities that it essentially had, right? That's where the definition of PTE comes, page table entry. Essentially what it does is it takes a specific compression size, right? And it will, I know it's a lot of words, but essentially it'll compress it, it'll identify, right? Whether it's compressed or not, and then it'll break down into subcategories, which algorithm was used, if it's FPC, if it's BDI, as well as the size of the compressed size. As Jay shrew, if it was 16 MB megabytes, or figuring out how we can layer it and figure out what's the ideal number, right? Next thing you know is essentially the page size remains still the same, right? Which helps when it has, essentially no new page sizes, right? Which avoids fragmentation, right? It doesn't get split up, it doesn't get messy. Essentially, it helps create a flow process that essentially has stages, basically, right? And as mentioned before, it does help offset the variable size, right? This takes the point of the image of the one that, the one that we did here, right? And the one with the train that Jay showed. When you go to a train, right, everybody's different sizes, everybody's different heights, everybody has different features about them, right? We essentially take that out of the equation and break essentially everything the same. And if they don't fit, we just put them in a different compartment, so on and so forth. That way we can figure out in stages who identifies where. Are you with us? Are you compressed? Then you stay here. If you're not compressed, you're an exception. And then the exception data is a third level. And one of the biggest, obviously, points of this paper is, when compressing pages, it has obviously a direct correlation with both bandwidth and latency, right? The best way I can describe bandwidth is, I'm pretty sure you guys all know either 400 or 85, right? The highway system, right? Each of the different lanes are possible entry points for the data to flow, right? The latency is how long it takes to go from point A to B, right? With this previous approaches, it has to constantly get compressed and goes back and forth with the DRAM. That causes a lot of lag, and obviously with time and efficiency and energy, right? This compression algorithm essentially helps prevent the necessary need to go back and forth, right? And even with that, the formatting that Jay had explained with the constant hits, right? Since it's broken up into 3 different subcategories and regions, it's all basically locally oriented, right? It doesn't have to constantly communicate back and forth the DRAM. Since there's subsection 1, subsection 2, subsection 3, and essentially the DRAM is the last layer essentially of defense that it has to go. It's not in Q1, it's not in Q2, and goes to Q3, and if it doesn't need to, then you go to Q4, which is obviously the DRAM in this case. All right, next slide. And one thing about particularly this approach with linearly compressed pages is that it's kind of algorithm agnostic, right? Essentially, the LCP is essentially an architect, right? But these different algorithms are the tools that we end up using to identify both the compression rate and obviously the performance that it provides, right? The first algorithm we have here is frequent pattern compression, which Jay had mentioned before, right? The issue, there's not an issue per se, but the main focus is that FPC follows is basically, it focuses on both zeros, small integers, and repeated bits, right? The thing with FPC though, however, it is the decompression latency is about 5 cycles, right? It's not that bad, but at the same time, it could be better, right? And this is typically ideal for structured data, right? If you have like either specific pattern recognition, some numerical projects, right? Then we have BDI. This is known as base delta immediate, right? This is a bit more numerical and a better approach compared to the 2 algorithms, even though it's algorithm agnostic. Statistically speaking, this one is better. And the reason why I say that is the B essentially helps store a specific base value that all of it follow. And everything else becomes small deltas associated with the original base, right? And on top of that, this specific base data delta immediate works really well with bandwidth sensitive workloads, right? Anything that has to do with helping compressing data from about to roughly 16 to 32 bytes, which makes it easier to either move, which makes it easier to work with, to transfer, to identify. And one of the best pros factor is the decompression latency being 1 cycle. And I know you're gonna be like, oh, it's only a 4 cycle difference, right? But when you constantly go back and forth, it adds up, right? And that's why typically the latency is much lower than FPC, which helps make things run faster for this approaches. Next. All right, as we described before, what is metadata cache, right? Essentially, it's data of the data, right? The main points within the metadata cache is it helps identify and break down which cache is associated with which, right? See, you have EBITs, right? Which lines are exceptions, right? It kind of breaks down the already data further to help identify and make it easier to locate it via the cache or just identifiable in general, right? Then you have, E indicates obviously location of the exception, right? And obviously it helps have different compression parameters, right? The way I look at it is honestly the way I put it right here is the table of contents, right? It's your table of contents for your data. It breaks it down further and further. So if you want to identify one specific pattern, if you want to find the location, what number was exception, it helps break it down in a much more detailed approach, right? Again, we're back into the same profit with hit rate. Since everything is temporal locality, right? Everything is local and pretty much, reduced down to the size where it's pretty much it's the same thing. It makes it easier to get almost roughly about 88 to 90% hit rate with the MD cache. So essentially, you don't have to keep going back and forth with DRAM because you're getting almost 90% of hits, right? But then another thing is, not another bad thing, but one of the practicality and the use cases of LCP is that it avoids designs like the RMC FPC because it doesn't have to go back to the DRAM. It has subsections like 1, 2, 3, and detailed to a point where it's able to identify rather than having to go for DRAM. Imagine you have to go from this door to this door, right? If you have a middle point, you don't have to constantly go back and forth, which will waste speed, time, and energy. Next slide.
Here we explain how LCP fits into the existing paging system in order to manage compressed. So, sorry. In order, like I was saying, in order to manage compressed pages, LCP adds 4 small fields to each PTE. These 4 additional fields are CBIT, which it tells us if the page is compressed or not. Then we have C-type, which identifies what compression algorithm was used. Then there's C-size, which tells us the how big the compressed page is. And lastly, there's C-base, which indicates the alignment of the compressed page. The important part is that these additions are very small and require minimal operating system changes. So the TLB can also store these fields without any issues. Thank you. And that's, those bullet points is basically what I already said, okay. This means we don't slow down the L1 catch or affect the critical CPU path. Overall, as I previously mentioned, the operating system and the TLB changes are pretty minimal, but they allow LCP to work smoothly with with the existing memory system. With all that being said, I have another quick question. What do the new PTE fields, as I previously mentioned, once again, the CBIT, C-type, C-size, and C-base, what do they actually help with? I didn't hear it. Did anybody answer?
Data identification or quickly finding the data.
I'm sorry, could you say that again?
He said data identification or quickly finding the data.
From the lines.
Yeah, so they help the system. It tells the system how the page is compressed, so the memory controller can correctly locate, decompress, and manage each page. So in this slide, it shows the basic reflow of LCP. When the system needs a catch line, can you click, please? When the system needs a catch line, the first step is computing the offset. Because every compressed line has the same size, this is just a quick calculation and is basically the index times the compressed size. After that, the memory controller fetches that compressed line from memory and decompresses it. Yes. But if the metadata shows that this particular line is an exception, meaning it couldn't be compressed to the fixed size, then the controller redirects the request to the exception storage, and it fetches the uncompressed line from there instead. Once the correct line is retrieved, whether the normal way or through the exception path, the read is complete. The key point here is that the fast path, which is like the green arrows, it's extremely common, and exception path only kicks in occasionally. Next slide, please. In this slide, here we show what happens when the system writes a catch line back to memory. The first step here is trying to compress the new catch line. If it successfully fits in the target compressed size for the page, then the controller just overwrites the old data in the compressed region and then writes it and it's done. That's the common case. If the line doesn't fit the target size, then it becomes an exception in that case. And the controller stores it in the exception region instead, and it updates the metadata so the system knows this line now lives outside the normal compressed area. Once the metadata is updated, the write is complete. And the main idea here is that LCP handles the writes cleanly, and only small portions of writes, a small portion of the writes need to go through the exception path. Okay, you can move on. So I can go ahead. Okay, now let's look at what happens when things don't fit perfectly. Once LCP normally works very smoothly, but there are 2 rare overflow cases that the system has to handle. The first one being type 1 overflow. This happens when the exception region becomes full. So when this happens, too many catch lines couldn't be compressed to the target size. And when that happens, the system needs to move the page to a larger compressed format or just relocate it. Then there's the second case, which is type 2, which is even more rare. This is when the total size of the LCP becomes bigger than the original uncompressed 4KB page. And if that happens, the page just isn't worth compressing anymore. So the system just falls back to storing it uncompressed. To avoid these costly situations, LCP introduces overflow prevention policy that tries to stop pages from reaching these states in the first place. The important thing here is to remember that these overflows are extremely rare, but the framework still has clean ways to handle them whenever they occur.
Another thing is apparently there's not like waste of the papers in the report, there's about only a 3% overflow situation. It's really rare that it has to go to the last tier of defense. It essentially, identifies if it's uncompressible, then obviously if it overflows, it's only about 3% chance.
Here, this slide just gives a quick overview of how the authors evaluated LCP. Since there's no real hardware implementing LCP yet, they used a simulation platform to model how it would behave in a real system. They tested LCP across a wide range of workloads to make sure the results were biased towards any specific type of application. They then measured several categories of metrics. Performance metrics shows how much faster programs run with LCP. Capacity metrics, it shows how much more effective memory you gain from compression. Then we have bandwidth metrics, which captures how much less data needs to be moved across the memory bus. And then there's energy metrics. Together these, I'm all over the place. Then we have energy metrics, which is the highlight of how much power the system can save. With all these categories, it gives a complete picture of LCP and its real impact.
So there is no specific software or hardware for implementing LCP. So they are doing it on the simulation platform. And now we're gonna see all the workloads results that they have performed on. It can be different. We'll see. So now this is the results part, right? Ending it soon. So how well does this actually works? So as you can see, these are some different workloads all the way in the bottom, and it's the main memory compression ratio. As you can see that the ZPC, RMC, FPC, LCP, MXT, LZ, LCP, BDI. So if you look at the MXT, that was the first approach results going to be here. Then the LCP had two different versions, which Anthony talked about, which was FCP and BDI, which is here. And then the second approach was RMC, FPC is also here. And then rest, they just did the workload on, but we didn't go further deep into those approach. And as you can see, the LCP BDI average is 1.62 compression. That's really more than the previous approaches. RMC, FPC had it, which was 1.59. As you can see, those bars represent those compression ratios.
Sorry to interrupt. I have one question. Why the MXT bars are higher as compared to the approach which the paper has given?
So that's kind of true that MXT does have the high ratio here. Because if you look at it, the MXT color, it's dark, and if you look at the dark color, it's just after this white line, which is the last one, and then the LCP comes. But we gotta make sure that the paper authors never meant to try or never tried to do the best one. So MXT is like a Ferrari, it comes expensive because you got a manufacturing cost for specific building that within the hardware. And then the LCP is like a Toyota. It's don't take that hardware designs or it don't take anything else. It's just simple process which can be done without using any extra things. And the author's purpose was never about building the highest compression ratio, but building it without using any physical hardware in a sense. So I guess I can.
Especially like compromising with bandwidth and latency as mentioned. If you pay the price, that's a good point that you made about MDX. Because even in the article, right, there's some aspects where MDX is good, right? But the thing is, the hardware and the energy costs, they kind of downside the point of it, right? Who wants to spend more? I mean, it's nice to have a Ferrari. I'm not gonna lie, I would want one too. But realistically, based off companies in budget tier, a Toyota's more practical or Honda. I know exactly. Bugatti costs $25,000 for.
Okay, so here what actually means all this graph thing, right? So when I say that it's 1.62% compression rate, it basically converts that your 8 GB RAM that comes in your laptop to 13 GB without using anything. So it's good. And then maybe not that good because there can be always something better, right? And then by workload, if you'll see, as you can see, like those are some like top compression ratios here, right? Those are the platforms which have scientific data. So you have lots of numbers or lots of zeros, which is repetitive. And when it's repetitive, it's easier for algorithm to predict and keep it in the main place compared to those which use like the web browsing data. So it says my last bullet point, right? Scientific sparse data is a huge win, but the web browsing data, not sure. Like it's good, but not that good. Okay, now it's like, so the compression ratio is going good, but does it make your system faster? Like that's the main purpose, one of the purpose of this paper. I mean, this approach in a sense. So it says in a single core, 6.1% faster. It sounds small, but it says you're 3.7 minutes per hour. And that hour, imagine like whole day, you're saving few half hour, and then it goes for billions. So it can save a good amount of time. The 2-core is 13.9% faster, and that's like really good. Really good. Let me just give you. So if you want to understand what is fast here, this is basically all these 3 different algorithms was used on this platform to see which ones works faster. And if it goes more than 1, then it's really good. Like it's faster. If it's less than 1, it's not that fast. Just wanted to make sure you understand the picture. As you can see, the geo mean, it's somewhere near 1. So if it goes more than 1, it's fast. And it can be different for different platforms. And one more things to add, right? We talked about BDI and FPC, that BDI is 1 cycle is equals to FPI is 5 cycle. So in the long term, BDI is better because we are comparing like the 3 different LCP, FPC and LCP BDI in a sense. So just wanted to.
Oh,
wait, this is one. And then here we have exceptions, which is like typically happens 17 per page, which is not that much, and the overflow, which we talked about the 2 different types of overflow and 1 policy. It happens 100 per 1 billion, which is negligible. The type 2 overflows never happens in their test data, so we don't know if it's happening or not. Next, please. And then this is the same thing which says that, which is describe what the overflow was, in a sense. Next. And this is the picture of those overflow compared to, what was it? I think this is the overflow, my bad. This is the overflow. Yeah, and you can see the numbers. This is negative billions, which is happens really less. As you can see the number. I don't know why they didn't show the number there. That's like here we are writing the number. This is not our picture by this paper.
All right, let's look at the numbers in terms of the big 2 things that we're looking at, right? The bandwidth, you have energy, and you have latency, right? As mentioned before, none of this is practical. As you mentioned, MTX is good. Why? Because these are all simulations. this isn't something that hasn't actually physically implemented, which if it does, it might be better. That's what's happening. Okay? One thing we always want to see is looking at numbers, right? As we mentioned before, right? Across average on both the VDI one, FPC one, there's about a 24% of bandwidth reduction, right? Oh, I'm sorry, I forgot. Where's the
I don't know.
I'm sorry.
I don't know.
Sorry about that, guys. So yeah, we've been able to identify across all three different variations of LPC that there's about a 24% bandwidth reduction on average, right? And yeah, it may seem, especially when you're looking at energy saving, it's only about 10%, right? But if you're able to save about 25% in bandwidth and about 10% energy costs, it makes it more viable as an option to use compared to the Ferrari example. But as you can see, across the different workloads, we see on average about a 40% bandwidth reduction, right? This is pretty big, especially for, a lot of memory-based applications and use cases, right? And another one good thing about it is it essentially helps compress a 1 DRAM burst of 64 bytes, for example, into 3 or 4 compressed lines, right? Essentially, imagine you're taking one approach to go to DRAM, right? But simultaneously, you're breaking it up into pieces, 1, 2, 3, and about 4 times. So you're getting about 4 times worth of your visitation to the DRAM, right? So that itself helps. And obviously the text metadata that is going to be limited. This is kind of a continuation of what Jake had mentioned, especially when you're looking at stability over time. Essentially what the slide's talking about is how does this run over across a large scale of numbers, right? That was a point of the inclusion of running it across a billion, okay? Just to track exceptions from the overflows, trying to determine what is the catch, right? When we're looking at it, right, especially since it's measured every 100 million, over 1 billion instructions, and with that, we were able to identify there's no significant degradation during that extensive period, right? But within that run, we're able to see that not only impacted it, right, but the 3-step process helped mitigate and prevent overflow, right? But another thing to note, right, is that this is mainly compressed between the 5 and 12 bits, the 2 KB rate, right? This helps, especially for data sparse applications, which helps achieve extreme compression with any 0 KB. Essentially, this idea helps in not as extensive base distributions, which makes it easier to compress it while maintaining the 4 KB, right? And also, we're always trying to get close to 0 KB optimization, right? It helps with. And yeah, this is kind of a breakdown of both 2 different approaches that we've mentioned, as well as LCP, right? And I know what you're going to say. All it does is showcase it, better than MSP. You also have to count that this is all smooth. It's on paper, it's going to look good, right? But only when you test drive it is it going to look good. So as you can see, obviously, we can see with bandwidth reduction, the main thing we're looking for, we can see obviously 24% PKPI reduction, right? As we know, it's algorithm agnostic, right? Since it's the architecture, it's not dependent on the tools that they use to make it run, right? And also, the energy efficiency, right? We just figured out, especially with the MXT, it has high energy and high hardware cost, right? It's expensive both to maintain it and even keep it. And on top of that, the performance gauge, you can obviously see that you can see the difference between about 6 to almost 14% difference in. Okay. So this is one thing that we needed to look at is if LCP looks good on paper, why do we simplify, right? The thing is, even LCP has its own shortcomings and faults. One of the main things is that it's really bad for metadata locality, right? If it's going back and forth to NRAM, multiple things, it's not as great of a, right? Because LCP is really good for local based things, going from 1 to 2 to 3, and without having to go to 0. But obviously, certain applications, certain requirements will have, a specific parameter of having to go back to communicate with different applications, right? And especially with the low compressive workloads, applications with incompressible lines and increasing exceptions,
obviously is a bad thing. The whole point of the paper is to try to limit exceptions and overflow. And as mentioned before, this is all based on simulations, right? None of this has any real life experience that we can actually test, right? From when we run it from a program, we're only getting numbers that inform the simulation, right? And obviously, another thing to note is its fixed size.
Anthony, I'm so sorry to cut you off. Is it possible for you to get closer to the mic?
Yeah. Another thing to note is the LCP's fixed size constraint, right? Between 512 base and 4K this flexibility, something that's either that doesn't fall within the range. So it doesn't fall within this, it's kind of hard to use that approach, but if it does, you got your answer of what you need. Yeah. So essentially, this is kind of a few key takeaways of why LCP. What's the point of using it, right? Obviously. Yeah.
Is it off? Hello?
There'll be green light.
Oh yeah, green light's on. Okay.
We can hear
Yeah.
you now.
Okay, you can hear. Okay. Why LCP works, right? Essentially, since exceptions are obviously rare and inexpensive to track, right? It helps help with obviously latency and bandwidth. And on top of that, the performance impact that it has is obviously pretty much higher for the memory capacity, as mentioned before, the bandwidth and the memory energy. So overall, the mechanism is simple, it's effective, it's like your average day Toyota.
Okay.
So as of, can you hear me? As effective as LCP is, the authors also pointed out several areas where it could be improved. The first one being policy level enhancements. These are basically smarter decisions about when to compress pages and how to handle exceptions and how to choose the best target sizes based on the workload. Then there's hardware and operating system optimizations. Even though LCP only requires small operating system changes, there's still room for the hardware and operating system to coordinate better. Another area is ecosystem integration. For LCP to be widely adopted, it would need support across different parts of the system, like compilers, memory controllers, and even future architectures. And finally, we have implementation considerations. This includes practical issues like designing efficient metadata caches, choosing compression algorithms, and validating all of this on real hardware instead of the simulations. So overall, LCP is already strong, but these improvements could make it even more flexible. Next page, please. To wrap everything up, the key idea behind LCP is really simple. By forcing all compressed lines in a page to be the same size, it makes memory compression both practical and efficient. This one change removes most of the complexity that caused older compression methods to fail, while still giving big gains in capacity, bandwidth, and energy savings. LCP isn't perfect, but there are still some corner cases and implementation challenges, but it provides a strong foundation for building real hardware systems that use memory compression effectively.
A couple questions. Prof. Pizza might be a little cold, but pizza. Why do previous memory compression methods fail, and what makes LCP simpler?
They didn't fail, but they were slower.
Yeah. Any takers?
We have this for both fixed and
I mean, all of them gonna have it.
different compression time.
Huh?
We have models with different size of files of the compression.
The main thing is like the operating system integration, right? That's the biggest key point that we have is it's really flexible depending on not a specific parameter, right? That's where we can either pick or the system can identify how small we want to make it and then proceed from the compression. So the thing with their previous examples is it's specific into this. It's either it does it or it goes straight to the DRAM, right? The whole point of LCP has multiple fail safes so that if it say it's compressed, then if it's not compressed, then it becomes an exception. If it's not an exception, it becomes an overflow if more exceptions happen, if that makes sense. Are exceptions and overflow events a serious problem for LCP?
Yes, no, guys. No, right.
No. Who said yeah?
Any questions for us?
We
have spoken about read and write. This is a good classic example of, I think, computer architecture problem. Addressing is always challenging. We understand. And when we prepare addressing machines, right, that is not easy. Now, what happens when, I think you spoke about read and write operations. What happens when atomic operation comes? Does that go to rank 0, 1, 2
Can you give an
groups?
example in a sense I can?
I think atomic operation is when you're trying to read and write on the same address, right? Effectively.
I haven't read about that thing on the paper, so I don't know. We'll get back to you. No. I'll be honest.
What do you think happens when a workload doesn't how might
Since it's already comprisable in bytes, if you're typically won't end up having to be an issue because it's already pretty much between the cache 1, 2, and 3. It identifies the least compressible size, right? And then from there it identifies how you want to approach it. If that makes sense. Not necessarily, since that one example I showed you, right? It takes one simple approach to go to the DRAM and breaks it off in typically about 4 breakers, right? So each breaks reduce the amount of time that it has to go to DRAM, right? That improves latency and bandwidth and performance in itself and energy costs. So it's kind of like a checklist for each category. If that makes sense.
All right, guys.
Thanks, guys.
Say, can you just be honest here? If you answer any question, can you just raise your hand just for 1 minute? If you have answered it, just yeah, I answered.
Because you're going to give us.
We have enough pizza. We have enough pizza.
We have participated here as well.
I mean,
raise it higher. Why are you not trying harder the first time, bro?
There's 2 hands there, 2 hands there.
1, 2, 3, 4, 5, 6, 7, 8. It's 8 or 9, right? So those people can take 2